Winter 1944 brought systematic flight testing of the captured Corsair as German engineers attempted to understand every aspect of its performance characteristics. Test pilots from Erprobungsstelle Rechlin conducted comprehensive evaluations, measuring speed, climb rate, maneuverability, and operational range under various configurations and altitudes. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The results contradicted fundamental assumptions about fighter aircraft design that had guided German development since the war's beginning. The Corsair demonstrated that American engineers had solved problems German designers didn't realize existed, achieving performance through engineering approaches that German industry had never seriously considered. Flight testing revealed the Corsair's exceptional speed characteristics across all altitude ranges. At sea level, the fighter achieved speeds exceeding 370 miles per hour, performance that matched or exceeded Germany's best low-altitude interceptors. More impressive was high-altitude performance, where the two-stage supercharged R2800 engine maintained power output at altitudes where German engines lost effectiveness. At the Corsair's optimal altitude of 19,900 feet, test pilots recorded maximum speeds of 417 miles per hour. This performance exceeded any production German fighter then operational, including the latest Messerschmitt Bf 109G variants and Focke-Wulf 190D models that represented Germany's most advanced single-engine designs. But German intelligence reports described even more capable Corsair variants entering American service. The F4U-4, powered by an upgraded R280018W engine with water injection capability, achieved maximum speeds of 446 miles per hour at 26,200 feet altitude. This performance represented a quantum leap beyond anything German industry could produce. German test pilots who flew the captured F4U-1A reported flight characteristics that challenged every assumption about proper fighter design priorities. The Corsair climbed at 3,250 feet per minute, a rate that exceeded most German fighters despite the American aircraft's greater weight and complexity. The fighter's roll rate proved exceptional, particularly when rolling in the direction of engine torque. German pilots noted that the Corsair could execute rapid direction changes that would be impossible in German fighters of comparable size and weight. The aircraft's control responsiveness remained effective at high speeds, where German fighters often became heavy and sluggish. Perhaps most impressive was the Corsair's dive performance. German fighters traditionally excelled in diving attacks, using superior acceleration in vertical descents to compensate for other performance limitations. The Corsair matched or exceeded German dive performance while maintaining control effectiveness at speeds that would cause dangerous compressibility effects in German aircraft. The structural examination revealed engineering philosophy differences that explained much about American versus German approaches to fighter design. German engineers traditionally optimized for specific performance characteristics, accepting compromises in other areas to achieve theoretical maximums in priority categories. The Corsair demonstrated a different approach that prioritized overall capability balance. The airframe structure incorporated design margins that German engineers initially considered wasteful. Components were built stronger than immediate requirements demanded, using more material and weight than German calculations suggested necessary. This apparent overbuilding provided growth potential that enabled the basic design to accommodate more powerful engines and increased combat loads without fundamental redesign. The wing structure particularly impressed German structural specialists. The massive main spar could handle loads far exceeding those imposed by the original R28004 engine installation. This design margin enabled later variants to use more powerful engines, producing up to 2,700 horsepower without requiring structural modifications. German fighters, by contrast, were typically optimized for specific engine installations with minimal structural margins. Upgrading to more powerful engines required extensive airframe modifications that often proved impossible within production constraints. The Me-109, despite continuous development throughout the war, remained fundamentally limited by its original structural design that could not accommodate significant power increases. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Corsair's fuel system demonstrated American engineering sophistication that German designers had never achieved. Self-sealing fuel tanks used multiple rubber compound layers that automatically sealed punctures, preventing fuel loss during combat damage. The system added weight and complexity, but provided crucial survivability advantages that kept damaged aircraft operational. German fighters largely lacked comparable fuel protection systems due to material shortages and manufacturing complexity. German pilots frequently faced catastrophic fuel fires when their aircraft suffered even minor combat damage, forcing tactical approaches that minimized exposure to enemy fire rather than accepting damage and continuing combat operations. The electrical system powering the Corsair's extensive equipment represented another area where American design philosophy differed fundamentally from German approaches. Comprehensive electrical generation and distribution systems provided power for radios, navigation equipment, gun charging systems, and cockpit lighting simultaneously, without overloading generators or causing system failures. German aircraft electrical systems, by comparison, often proved inadequate for their equipment loads. Pilots learned to operate systems selectively, turning off radios to power gun systems or disabling navigation equipment to maintain cockpit lighting. These limitations forced tactical compromises that reduced combat effectiveness. The cockpit layout itself demonstrated American understanding of pilot workload management that German designers had not fully grasped. Controls and instruments were arranged for maximum accessibility and logical operation sequence. Engine monitoring gauges provided comprehensive information that enabled pilots to optimize performance and detect problems before they caused failures. German fighter cockpits, while functional, often required pilots to manage complex systems through awkward control arrangements that increased workload during critical combat phases. The difference reflected American civilian aviation experience that emphasized pilot efficiency and safety through thoughtful design, rather than expecting pilots to adapt to poor ergonomics. The manufacturing quality visible throughout the Corsair provided perhaps the most sobering evidence of American industrial capabilities. Every component showed consistent precision and attention to detail that German factories could no longer achieve under wartime conditions. Aluminum surfaces were smooth and properly finished. Steel components were correctly heat-treated. Fasteners were precisely manufactured and properly installed. This quality consistency reflected manufacturing systems that could maintain standards while producing enormous quantities. American Corsair production totaled over 12,000 aircraft by war's end, with quality that remained consistent from the first production examples through the final deliveries. German industry struggled to maintain quality for much smaller production runs while dealing with material shortages and facility damage. The propeller system examination revealed manufacturing sophistication that particularly impressed German engineers. The Hamilton Standard hydromatic propeller incorporated complex hydraulic control mechanisms with tolerances measured in thousandths of an inch. Internal passages, rotating seals, and control valves all required precision manufacturing that German facilities could not achieve consistently. German propeller technology lagged significantly behind American developments, forcing German fighters to use simpler constant-speed designs that provided adequate performance but lacked the optimization capabilities of American variable-pitch systems. The manufacturing precision required for advanced propeller designs exceeded German industrial capabilities even before the war began. Engine testing provided the most comprehensive evidence of American technological superiority. The Pratt & Whitney R2800 double WASP represented engineering excellence that German manufacturers could not duplicate. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower reliably. The engine's construction showed manufacturing capabilities that seemed almost incomprehensible to German specialists. Cylinder machining achieved tolerances that German factories struggled to maintain even with their best equipment and most skilled workers. Surface finishes on critical components exceeded anything German industry produced routinely. The two-stage supercharger system particularly challenged German understanding of manufacturing feasibility. Complex internal ducting, precisely fitted rotating impellers, and sophisticated control mechanisms all required machining and assembly techniques beyond German capabilities. German attempts to develop comparable supercharger systems had failed due to manufacturing limitations rather than theoretical knowledge deficiencies. Perhaps most revealing was the engine's operational reliability. American radial engines operated at their rated power for hundreds of hours between major overhauls. German engines, even when newly manufactured, often failed to achieve their theoretical power ratings and required frequent maintenance to prevent failures. The difference lay not in design concepts, but in manufacturing precision and materials quality. American metallurgy had developed techniques for producing components with consistent properties and reliable performance. German materials science, while theoretically advanced, could not be translated into production reality under wartime constraints. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By spring 1945, as German forces collapsed on all fronts, the examination of the captured Corsair had revealed truths that German aviation specialists found impossible to ignore. American fighter development had progressed far beyond what German intelligence had estimated, achieving performance levels that German industry could not match even under ideal circumstances. The F-4U-4 Corsair, entering widespread service as Germany surrendered, represented the culmination of American fighter development during the war years. With its upgraded R2-80018W engine producing 2,450 horsepower under war emergency power settings, the fighter achieved speeds of 446 miles per hour at optimal altitude. This performance figure represented more than impressive specifications. It demonstrated American capability to design, manufacture, and deploy fighter aircraft with performance characteristics that rendered German fighters obsolete, regardless of pilot skill or tactical doctrine. The mathematics of aerial combat had been fundamentally altered by American engineering excellence. A fighter capable of 446 miles per hour possessed overwhelming advantages in every aspect of air-to-air combat. It could engage enemy aircraft when conditions favored victory and disengage when they did not. Enemy fighters, regardless of their armament or maneuverability, became irrelevant if they could not force engagement with opponents who controlled the tactical situation through superior speed. German test pilots who had flown the captured F-4U-1A understood these implications with painful clarity. Even the earlier Corsair variant they had examined could outrun any German fighter in service. The newer F-4U-4, with its nearly 30-mile-per-hour speed advantage over their captured example, would dominate aerial combat through velocity alone. The climb performance of American fighters provided equally devastating advantages. The F-4U-4 climbed at 4,170 feet per minute, a rate that exceeded any German fighter by substantial margins. This capability enabled American pilots to gain altitude advantage rapidly, the critical factor that determined the outcome of most aerial engagements. German fighters, even the latest high-altitude interceptors like the TAR-152H, could not match American climb rates at the altitudes where most combat occurred. German pilots would find themselves perpetually at disadvantage, fighting from below against opponents who could dictate engagement terms through superior altitude performance. The industrial implications proved even more sobering than individual aircraft performance. American production capacity had enabled simultaneous development and manufacture of multiple fighter types, while maintaining quality standards that German industry could not achieve for single designs. The United States produced nearly 50,000 Corsairs, while also manufacturing tens of thousands of P-51 Mustangs, P-47 Thunderbolts, and other fighter types. This production achievement reflected manufacturing maturity and resource availability that Germany never possessed. American factories could maintain precision standards while producing unprecedented quantities, supply allies through Lend-Lease programs, and continuously improve designs based on combat feedback. German industry struggled to maintain production of existing designs, while resources dwindled and facilities suffered bomb damage. The comparison grew more painful when German engineers considered the broader context of American aircraft production. The United States had simultaneously developed heavy bombers, transport aircraft, training planes, and naval aviation, while maintaining fighter production at levels that exceeded total German aircraft output across all categories. American industry achieved this production miracle while maintaining living standards that exceeded those of any combatant nation. American workers earned wages that enabled comfortable living while producing weapons that would determine the war's outcome. German workers, by contrast, faced increasing hardship as resources were diverted to military production that proved inadequate against American industrial might. The captured Corsair represented not just superior technology, but the product of an economic system that could outproduce its enemies, while maintaining technological advancement and quality standards they could not match. German engineers examining American manufacturing techniques understood that they faced not just better aircraft, but an entire industrial civilization oriented toward victory. As Allied forces overran Germany in the final months of the war, personnel at Erprobungsstelle Rechlin prepared for evacuation. The facility that had served as Germany's premier aviation testing center since 1926 faced abandonment as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed technical documentation and prepared to destroy equipment that could not be evacuated. Some captured aircraft, including at least one of the Corsairs, were pressed into improvised service with combat units, desperately defending the approaches to the capital. These aircraft provided one final comparison under actual combat conditions between American and German engineering approaches. The Corsairs continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. German fighters, including Panthers and the few remaining Tigers pressed into ground attack roles, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. The story of the captured F-4U Corsair at Erprobungsstelle Rechlin represents one of the great technological disparities of World War II. German engineers, working within an industrial system that prioritized theoretical performance over practical utility, had produced aircraft that looked impressive in specifications, but failed to achieve the fundamental requirement of military equipment: reliable operation under combat conditions. American engineers, applying decades of civilian automotive and aviation experience to military requirements, produced aircraft that achieved exceptional performance through sound engineering principles and manufacturing excellence. The Corsair didn't succeed through revolutionary technology, but through the systematic application of proven techniques to create a fighter that worked reliably under the demanding conditions of aerial warfare. The 446 mph maximum speed of the F-4U-4 variant represented more than engineering achievement. It symbolized American industrial maturity and manufacturing sophistication that enabled the reliable production of high-performance equipment at unprecedented scales. German industry, despite its theoretical knowledge and scientific expertise, could not match American practical capabilities. The lessons learned through the examination of the captured Corsair extended far beyond aviation technology. German engineers confronted evidence that American industry had achieved manufacturing maturity that enabled superior products across all categories of military equipment. The gap between American and German capabilities reflected not just resource availability, but fundamental differences in industrial development and engineering philosophy. American success resulted from decades of civilian industry experience that emphasized reliability, maintainability, and production efficiency. These priorities, developed through commercial competition, proved equally valuable for military applications. German industry, lacking comparable civilian development, could not translate theoretical knowledge into practical manufacturing capabilities under wartime pressures. The examination of JT-404 at Rechlin provided final confirmation of American technological superiority that German aviation specialists had suspected but hoped to overcome through superior design or tactical innovation. The evidence proved that hope misplaced. American engineers had not only achieved superior individual aircraft performance, but had done so through industrial systems that could maintain quality while producing overwhelming quantities. In armored warfare, as German engineers had learned through examination of captured Sherman tanks, the weapon that functions reliably when needed defeats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. The same principle applied to aerial warfare with even greater force. A Corsair, capable of 446 miles per hour, that reliably achieved that performance was infinitely more valuable than a German fighter with impressive specifications that broke down before engaging the enemy or required extensive maintenance for every hour of operation. Speed wasn't just a performance characteristic, it was the foundation of tactical flexibility that determined which force could impose its will upon the enemy. German test pilots, who had flown the captured Corsair, understood this reality with painful clarity. They had experienced flight characteristics that exceeded their own aircraft's capabilities in every meaningful category. More sobering, they knew that American industry was producing such aircraft by the thousands, while German production struggled with declining quality and inadequate quantities. The mathematical progression was inexorable and brutally clear. American fighters that could outrun, outclimb, and outmaneuver German aircraft would dominate aerial combat, regardless of pilot skill or tactical doctrine. German aviation had lost not through inferior courage or inadequate training, but through industrial and technological disadvantages that could not be overcome through willpower alone. The story of German examination of the captured F-4U Corsair stands as a watershed moment in aviation history, the point when one nation's engineers confronted another's technological supremacy and found it insurmountable. The 446-mile-per-hour speed of the F-4U-4 variant represented more than impressive performance figures. It symbolized American industrial achievement that had rendered German aviation obsolete. Post-war analysis confirmed what German testing at Rechlin had revealed. American fighter development had progressed systematically throughout the war, while maintaining production standards that German industry could not match even in peacetime. The Corsair's success stemmed not from revolutionary breakthroughs, but from the methodical application of engineering excellence to create aircraft that performed reliably under combat conditions. The lessons learned at Rechlin would influence post-war German aviation development when the Federal Republic began rebuilding its air force during the 1950s. German engineers consciously adopted American design, philosophies that emphasized reliability and maintainability over theoretical performance optimization. They studied American manufacturing techniques and deliberately applied them to European aircraft development. The examination of the F-4U Corsair, by German aviation specialists in 1944 and 45, stands as acknowledgement of technological reality that could not be denied or overcome through traditional German approaches. It marked the end of German aviation supremacy and the beginning of American dominance that would extend through the jet age and into the space era. The captured Corsair, with its distinctive bent wings and massive radial engine, represented far more than enemy equipment brought home for technical intelligence. It was tangible proof that industrial maturity and sound engineering principles, based on practical experience, mattered more than theoretical innovation pursued without regard to manufacturing reality or operational requirements. German aviation entered World War II with technical advantages in many areas, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained production while fighting enemies with superior resources and more mature industrial systems. The United States entered the war with aircraft that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality and performance, based on combat feedback. This approach, perfectly exemplified by Corsair development and production, proved far more effective than German technical sophistication applied to limited production runs. The 446-mile-per-hour speed, achieved by the F-4U-4 Corsair, represented the culmination of American engineering excellence, applied through industrial systems that could maintain precision while producing unprecedented quantities. It demonstrated that speed, properly engineered and reliably manufactured, was the decisive factor in aerial warfare that rendered other performance characteristics secondary. German engineers at Erprobungsstelle Rechlin had proven this beyond doubt through their examination of the captured F4U-1A and their understanding of more advanced variants entering American service. They wrote detailed reports documenting their findings and reached correct conclusions about American advantages. But understanding a problem and solving it were fundamentally different challenges that German industry could not meet under wartime conditions. The story ends not with German acknowledgement of American superiority, but with the broader recognition that industrial warfare demanded not just advanced technology, but the manufacturing systems capable of producing that technology, reliably at scale. The Corsair succeeded because American industry had developed both the engineering knowledge and the production capabilities necessary to create superior aircraft consistently. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.